So we're going to start today with something that some of you may have heard of and some of you may have never heard the word before, functional groups. If you were in my classroom, these would be hung up front where you can see. And I like to say the functional groups is where the action is, okay? They are atoms or groups of atoms that show relatively consistent properties when attached to different carbon chains. Alcohols is one that you might be familiar with. Alcohols are an OH. Well, there's a whole bunch of other ones: ethers, carboxylic acids, esters, aldehydes, ketones, amines, amides, and when you go to college, there's probably another 10 on top of this. Um, in functional groups, you'll often see the letter R, and that's not some special element that we've never heard of before. The R symbol represents a non-active hydrocarbon portion, okay? So it doesn't represent chain length. It can be a chain, it can be really long, it can have branches. There can be several functional groups attached. This R is just where it's attached in. So the hydrocarbon chain is usually unchanged during chemical reactions. So if you have a big long hydrocarbon chain and it ends in this, if a chemical reaction were to happen, this is probably where the chemical reaction's happening. This probably all stays about the same. The functional group is where this reactivity occurs because remember, we're going to have things like polarity happen there. We might have lone pairs. Things might be twisted in certain ways. That's why that's going to happen. The hydrocarbon part of the organic compound usually doesn't affect the nature of its chemical reactivity. Okay, so if you were to look at these three substances, it's got one carbon, two carbons, three carbons, all attached to a chlorine. They all undergo similar chemical reactions. They're all going to be represented by RCl, which, by the way, this is an alkyl halide. But the R group isn't something that we can totally ignore, right? Because it can actually have dramatic physiological consequences. For example, ethanol is found in beverages. Methanol, which you can see here is just one carbon different, can cause blindness and death. So this is like not something we can just ignore. Saturated hydrocarbons are where we need to start. This is the simplest of the organic compounds, okay? Saturated hydrocarbons are simply C's and H's, all single bonds. And the reason we call them saturated is because I like to think about them as having a saturation of hydrogens in all of these carbons. So you'll notice there's no double bonds. Alkanes are right here. They're non-cyclic. And cycloalkanes are cyclic. So alkanes are these saturated hydrocarbons. This is a table, the first 10 straight chain alkanes. You need to memorize this, okay? Now, before you get all scared, because this is big, remember that it just, every time you add a carbon, you need to add the appropriate number of hydrogens so that your carbon bonds 4 times. When you get here to pentane, these should be pretty easy. Pent is 5, hex is 6, 7, 8, 9, 10, right? These should all be pretty familiar. You probably have already learned those already. The first 4 are usually the trickiest to memorize. In college, I was taught meet Ethan, professional butler, for meet Ethan, professional butler. I don't know why, but that was 1, 2, 3, 4 carbons. So you're going to want to commit this to memory as soon as possible. If you are confused at the number of hydrogens, there's a formula you can use. There's basically a hydrogen for every carbon, and then there's 2 at the end. So you have 2 times the number of carbons plus 2 for the end, and I'll show you what that looks like drawn out, right? If you have this, you're going to have 2 carbons that come off of there, and then you're going to have, 2 hydrogens that come off of there, and then hydrogens at the end, which is why you get this formula to represent that. Now, if you have a cycloalkane, you don't need the 2 at the end. So you can just see this is just twice the number. So if you have C3, you just have H6. C4 is H8. So they're pretty easy to memorize. Now you might be wondering, why can't I just count these? Well, if I give you like C52, you probably don't want to be counting those out. So in the future, you're going to learn the functional groups. I know if you're in AP Bio, you've probably already memorized them. Maybe in AP Chem, you're memorizing them. But for right now, I just want you to know alkane, which are the ones we just talked about, alkene, alkyne, alcohol, and alkyl halide. So really quickly, alkenes have some sort of double bond between the carbons. Alkynes have some sort of triple bond between the carbons. Alcohols, like we said, have an OH, and alkyl halides, at the side of the periodic table, you've got fluorine, chlorine, bromine, and iodine. So the alkyl halides have one of those attached. So they're represented like that, or I've seen them actually represented with X's. So that's an alkyl halide. Here's a chart that has all of the functional groups summed up. Feel free to take a gander at this because you will eventually have to memorize them. But like I said, for right now, it's alcohol. And oh, there they are down at the bottom. I lost them. Alkenes, alkynes, and then alkyl halides. And they're right here. They're listed under halides. Those are the ones that you need to know for this chapter. Sometimes you'll see the word families in chemistry. I don't love this word. They talk about families down the periodic table, but they also might call the alkanes, the alkenes, and the alkynes families. Again, alkanes have all single bonds with this general formula we just talked about. That includes the cycloalkanes, this general formula. Alkenes have the double bonds, and alkynes have the triple bonds. If you ever get yourself confused between an alkane, alkene, alkyne, you've got the A, the E, and the Y, and they do go in alphabetical order for single bond, double bond, triple bond, if that helps you at all. If you look at the families here, you've got this alkane family that would include everything with all the single bonds. You could use the word family to describe the functional groups, right? So you could call this like an alcohol family, saying that it has all the alcohol functional group. Another word that you might see is a homologous series. They have the same functional group, but different numbers of the carbon groups, right? So this would again be a homologous series. This might be a homologous series. Members of the same homologous series have similar chemical properties. This is all exactly the same stuff I just said. It's just some different words to say it that you might see. Now, today I'd like to look at boiling and melting points. Okay, so remember that organics are mostly nonpolar, right? So they have relatively, and I like the word relatively low intermolecular forces. So organic solids, like we said, like candles, tend to be soft with low melting points. Organic liquids have high vapor pressure and therefore low boiling points. Vapor pressure is something that you may have forgotten from Chem 1. Vapor pressure is if I have a liquid sitting on a table, this liquid's vapor pressure is the pressure of the liquid trying to escape into the gas phase, into the atmosphere. Okay, so a high vapor pressure means that it will evaporate quickly and therefore has a low boiling point. Want to make sure you don't mix that up. Boiling and melting points of homologous series increases with the number of carbon groups due to more dispersion forces. Basically, the heavier the molecule, the more the molecule surface area, the more mass, the higher the dispersion forces, right? And if we increase the dispersion forces, we're going to make more IMFs or IMAs, intermolecular forces, intermolecular attractions, so more energy is needed to separate. So it'll have a higher melting point and boiling point. And what we've got here is just the melting point and boiling points of some straight chain alkanes, which are just the carbon groups. Here would be 1 carbon, 5 carbon, 10 carbon, 15 carbon. The boiling point increases. You can see the melting point's got kind of like a slow start, but it does exactly the same thing. They'll increase, and again, it's because of that increase of dispersion forces. Another thing that you can look at to find out boiling and melting points is branching. So boiling and melting points decrease. You will have a lower boiling and melting point when you increase the branching. And this is again because of dispersion forces. This one right here is more spread out and therefore will have higher dispersion forces and will have a higher boiling point. This has the same number of carbons, therefore the same mass, the same chemical formula. However, it's more branched, so it's a little bit closer together. We'll have less dispersion forces and therefore a lower boiling point. By the way, this is just to show you that this isn't always foolproof. Cycloalkanes have higher melting points than their open chain counterparts. Basically, they get kind of, if you have a bunch of cycloalkanes all stuck together, they will tightly pack together and they won't want to melt. Okay, so they make this kind of crystal lattice structure, not exactly like an ionic compound, but similar, and it won't melt. So it really, like it feels like almost the opposite of this. It's worth mentioning VOCs. VOCs stand for volatile organic compounds. And VOCs are volatile, which means that they evaporate quickly. And VOCs are highly branched. And VOCs are, bad for the earth, and they're released in toxic chemicals or in things that you might have around your house. And they, did some damage to the ozone layer a few years back. And we'll talk about that more during class. But this is the reason why, because they're highly branched, which makes them have lower dispersion forces and therefore higher volatility.